Hi, this lecture is called column space. We will review the definition of the span of a set with emphasis on the set form or made of the columns of a matrix. This span of the set of columns of a matrix is denominated as the column space. So this definition of the column space is telling us that every element in this set that we are calling column space, every member of that set is indeed a linear combination of the columns of a matrix A. Therefore, any element of C of A, as we write here, is going to have this form, right? This is another way of describing the span of a set of column vectors A sub 1, A sub 2, A sub 3, all the way through A sub n. There are n of these column vectors, and each of them is of the form scalar multiplying a column vector, right? So each term in this sum looks like this, and we just happen to have a sum that we call a linear combination. So that set of linear combinations of the columns is what we consider the column space of a matrix. So you have to check a little bit, pay close attention to the dimensions. We're assuming that A can be a matrix that looks like this, right? So it has m rows and it has n columns. So that means that each column of this matrix with m rows and n columns, I'm drawing here the column in green, pardon my imprecision there. Each column, which is this vertical stick here, each of those columns is a member of C sub m, right? So the length of that column, that matrix, is m. There are m entries. That means that any member, if we say that W is a member of the column space of A, then that means that W is a vector in Cm, a vector that has m entries. Okay? So now we have a theorem that tells us that we have a rectangular matrix A with m rows and n columns and a vector of constants, vector B of size m, then that vector B is a member of the column space of A if and only if the linear system that has A as a coefficient matrix and B as the vector of constants is consistent, right? So membership on a column space is the same as membership on the span of a set, which is a concept that we had previously reviewed and learned. So now we take note, we refresh our memory and take note that this issue of membership is something that's going to involve creating an augmented matrix. We put the matrix A, we put the column vector B, and then we are going to row reduce. So we create an augmented matrix, row reduce, and this would be providing the information for solution set and certainly consistency, whether or not the solution set is non-empty. Consistent, this means non-empty solution set. Inconsistency is something that we obtain from the RREF. There would be a leading one placed on the last column. If that happens, there would be a solution set that is empty, which implies there is no membership. Okay, so the column, the vector is part of the column space if and only if the solution set of this system is non-empty. In such case, there's a unique solution or infinitely many of them. So here we have an example, a matrix that has 3 rows, 4 columns. We have a candidate for membership that has length 3. And then we're asking the question whether or not this vector is a member of the column space. So is this vector a member of the span of the columns of this matrix? So we form an augmented matrix and explore this as if we were solving for a linear system of equations. These are all very familiar calculations, and the fact that here we're finding leading ones on positions different from the last column, right? So here's the last column of the augmented matrix, and you can see right away that there is no leading ones on the last column. The leading ones are here. This is telling us, this is right away indicating that as a linear system, this linear system with this matrix, the matrix of coefficients, and this vector as the vector of constants, this is consistent. This is a system that is consistent. And we could give explicit detail about the solution set. If we do so, we'll be finding specific values for alpha. Remember, the idea here is, can we write the vector, the given vector v, as a linear combination that looks like alpha 1, a1, alpha 2, a2, alpha 3, a3. In this case, this matrix has 4 columns, and then alpha 4, a4. So the key would be, what are the values of alpha for which we can represent this vector as a linear combination? And so by computing explicitly the solution set of this system, we would be able to come up with specific values of alpha. Now, and what I just mentioned is something that I am leaving as an exercise to you, the person that's listening to me right now and that's watching this. So it's left, if this were a book, I would say that calculation is left to the reader as an exercise, but you're not necessarily reading this, you're listening. So you're going to be an active participant. You can pause the video right now and complete that exercise and come up with your own values of alpha, of the scalars alpha, and that make that linear combination to be true. Now, let's suppose that you pause the video and you're back, and now we're exploring the question, is this vector W a member of the column space? And you can see right away that by forming the augmented matrix, right, this is the augmented matrix this is the matrix A we were working with, and now the only thing we're changing is the vector in the last column, this vector W, we row reduce, and this location of a leading one on the last column of the augmented matrix is telling us that this, as a linear system with that matrix of coefficients and that vector of constants, as a linear system, this is inconsistent, meaning the solution set here is empty, and therefore we conclude that no, the answer is this vector W is not a member of the column space. That vector W does not belong to the span of the columns. There is no way of finding values for scalars alpha 1, alpha 2, alpha 3, alpha 4 such that the linear combination would be exactly equal to this vector. So now let's review a theorem that we had learned in a different context, and now let's review this theorem in the context of the column space, and this has to do with coming up with given a set of column vectors, coming up with a subset of that set which is linearly independent and is also spanning. In other words, it has the property, it has both properties, it has the spanning property and the linearly independent property. Okay, and all we have to do is to rely on RREF, on the reduced row echelon form of the matrix, to be able to come up with this subset. So let's read the theorem. It says we have a rectangular matrix with columns A1, A2, A2, A3, A4, A5, all the way through A sub n. There are n columns. And we compute the RREF and find that there are non-zero rows in the RREF. Very importantly is this set of indices, the set capital D, in which we find that there are exactly R elements that are R indices in this set capital D. And this is all information that we're familiar with. And those are indices denoting the columns in which you may locate leading ones. And so now we select the subset that we want to build out of the general set of columns is a subset of columns that contains the columns with indices in this set D. In other words, select the columns that have leading ones, and that new subset will be both linearly independent and it would have the spanning property. So here we have this example. This matrix has 3 rows, 4 columns. RREF is computed here. R equals 2, right? So here we have that n is equal to 4, R is equal to 2. The set that we're calling D contains indices 1 and 2. In other words, we're going to be interested on columns A1 and A sub 2. This would be the set of columns that we would be interested in, and that set of columns, the set out of the original set of 4 columns, the set that contains column 1 and column 2 is a set that has the spanning property. In other words, the span, what we're saying here, that this column space is equal to the span of the set that contains A1 and A2. Okay, so the span of this set equals the column space, but also this theorem is telling us that this set with columns 1 and 2 is linearly independent. So we would say that that set with those 2 columns is a basis for the column space. A basis is a set that has both properties, the spanning property and the linearly independent property.